Welcome everyone. For today's prep, we're going to start looking at geometric series. So we'll first see what the definition of a geometric series is, and then we'll see how we can figure out when it's convergent and when it's divergent. And this is kind of the best part about these geometric series, we can actually figure out the sum if it's convergent. So let's start with the definition. And before we look through the definition here, let's actually remember back what we were doing in class the other day. We defined something called a geometric sequence. So this was kind of the general form for these geometric sequences was a times r raised to the power n. And a and r were just constants. And we looked at this sequence in quite a bit of detail. We figured out how to calculate the limit of this sequence depending on the r value. So we spent some time with this geometric sequence. And if we write out the first few terms of this, the first term is just a, the second term is a times r, the third term is a times r squared, and so on. So all we're doing with a geometric series then is we're taking this geometric sequence, a comma ar comma ar squared. We're taking this geometric sequence and we're attempting to add all of the terms together. And just like when we talked about geometric sequences and we calculated the limit, the ultimate convergence of this geometric series is going to depend on the value of r. Again, we want to think of convergence of a series as, can we actually add all the terms together? Now, this a value doesn't affect whether we can do that or not, but it does affect the value of the sum, which we'll see in a second. So this is one of the versions of the geometric series we're going to be looking at. A similar one just changes it so that the starting index is n equals 1. So in our definition here, we have our starting index at n equals 0, and then it counts up from there. Another way to write a geometric series or geometric sequence is to start your index at n equals 1, and that changes the formula a little bit to a times r raised to the n minus 1. But in that case, you still end up with the same list of terms that you're trying to add up. So it's really equivalent. All right, so what's so special about these geometric sequences or series? Well, we can actually figure out the sum. And this is the really cool part about these. So we can actually add all these terms together. And when we do that, we have this nice little formula that the sum is a divided by 1 minus r. So we'll probably look at where this comes from in class. But for right now, we'll just kind of take this as a formula to know. Now, this formula doesn't always work. It only works depending on specific r values. So we need the absolute value of r to be less than 1 for this formula to work and for this series to converge. If the absolute value of r is greater than or equal to 1, well then the series diverges. So we can't actually add all the terms together and get something usually meaningful. All right, so let's look at example 1. So we want to determine whether the following geometric series are convergent or divergent. And if they're convergent, we want to figure out the sum. So let's start by just kind of rewriting our formula here. Just to kind of keep this in mind. Actually, let's put it up here. Geometric series. We just want to remember the kind of our prototype here. A times r raised to the power n. So in this first example, we have this series going from n equals 0 to infinity. And then we have the terms of our series here are 5 times 1/2 raised to the power n. So we just want to kind of compare these two, the series we're investigating, with our kind of our prototype here. And we want to figure out what the a value is and what the r value is. So if we kind of match things up, we see that the a value looks to be 5, and the r value looks to be 1/2. And, well, really, the a value is going to, we do need to keep track of that, but really where we want to start off is we want to start off with this r value, because this really tells us if our geometric series is going to converge or not. And based on this value, it's 1/2. And we're allowed to say then that this is a convergent geometric series. With r equal to 1/2, and that satisfies the absolute value of r being less than 1. So the absolute value of 1/2 is just 1/2, and 1/2 is definitely less than 1. So that means this is a convergent geometric series. So when we do these, and later on we're going to be working with geometric series for quite a bit. So when we state that a series is convergent for this reason, we want to give a little explanation. And so for a geometric series, this is an adequate explanation. We're stating that it's convergent. We're stating that we've recognized that it's a geometric series. We've stated the r value, and then we've stated the condition that that r value satisfies. So when we explain why a geometric series is convergent or divergent, really this is what I would want to see. All right, well, since it's convergent, we can actually figure out what the sum is here. So the sum in our case, if we write down the formula, is a divided by 1 minus r. So we take our a value, which is 1, and then we get 1 minus r in the denominator, so 1 minus 1/2. And if we do that, we get 5 over 1/2, which is 10. So if we could add up all these terms together, we would get 10. All right, let's try another example. Let's look at part B. Now for part B, we have the series sigma going from n equals 0 to infinity, and we have the terms 1/2 raised to the power n plus 1. So when we deal with terms like this, and what we see when we look at this is we have a constant, and then the exponent there is n. It's an n term. But it's not quite. There's n plus 1. So it's not quite the same as the one we had before. And so in order for this geometric series, in order for us to use this formula, we have to get it into that specific form. So if n is starting at 0, we need the power there to be n. So that's one thing. One little thing to note. So because we're starting at n equals 0, we need this exponent to be n. All right, so what do we got? We have one extra power of 1/2 here that we got to do something about. So the idea is we can use our exponent rules, regular algebraic rules, to just kind of break this exponent apart. And when we do that, we're just going to peel off that one extra copy of 1/2. So we have n copies of 1/2 that we're multiplying by together, and then we're multiplying in one additional copy. So let's just kind of break that copy off and put it first. So then we'll have 1/2, and then another 1/2, but this one is raised to the power n. So I've taken that one extra 1/2 term in our geometric, the terms of our sequence there, and I've just kind of broken it off. I peeled it off and put it first. And so now this is the correct format. So now if we kind of match things up, I have that lone constant that doesn't have any n terms first. So that's going to be my a value. And then I have this constant, and it's getting raised to just the power n, which is the way we want it. Just like in our prototype here, we have the constant r being raised to the power n. So we can see that the r value here, 1/2. All right, so now we have all the information that we need to say what's going on. So the a value here is 1/2. The r value here is 1/2. And based on that, r value, we can determine if this is going to converge or diverge. So this is a convergent geometric series with r equal to 1/2, blah, 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 satisfying absolute value of r less than 1. So again, we want to, when we're dealing with geometric series and we state whether it's convergent or divergent, this is really the explanation that I want to see. So you're naming the series. We're calling this a geometric series. So we're going to see that there's other specially named series out there. We're stating what the r value is, and then we're stating the condition that tells us it's convergent. So because we know this is convergent, we can also figure out then the sum. So this is the a value divided by 1 minus the r value, and this ends up just being 1 once we simplify that down. All right, so we'll get a little more practice playing this sort of game where we might have to rewrite our expression a little bit before we exactly recognize that it's a geometric series. All right, so we'll see you then. Bye-bye.